How's it going, Wildcats? Welcome back. So what we're going to do today is collect the data for the rotational experiment that we started yesterday. Yesterday we had the basic outline of what was going to happen, and we also derived an equation for the rotational inertia. This is our apparatus that we've got, and this is the one that we collected some data with yesterday. You'll see that experiment here in a few minutes. So we take the projectile of physics, we fire a foam ball into this catching cup, and it starts to rotate like that. This sensor will collect the angular displacement versus time data for us. It would also get us the angular velocity directly, but we're not going to do that. We're going to just take the angular displacement versus time data and interpret the slope of that data to get the angular velocity. So it's a little extra skill that will practice that'll get us warmed up for linear kinematics and rotational kinematics. So this is our tool. I'll put that aside. So in our derivation, we've got the rotational inertia equation where we see variables of mass, separation, initial velocity of our point mass, the final angular velocity of the apparatus as it rotates, and that's it. So we need to be able to take data on those four things. So let's start off with data collection for the point mass. So what I have here is 28 point masses, projectiles of physics, and they have a mass present here of about 54 grams. You'll have to do a little conversion on your own for that. Make sure it's in kilograms. Next, we have the radius of the separation between the point mass and the axis of rotation, and as you can see, it's 14 inches. Now William will use the tool of physics to launch the projectile.
3, 2, 1, fire.
Now let's use the graphical analysis software to analyze the data we just collected.
All right, so this is the full data that we just collected. As you can see, on the vertical axis, we have angle, or the angular displacement, and on the horizontal axis, we have time. And so the slope of this line would be in radians per second. That would give us the angular speed, or the angular velocity of our apparatus as it rotates. As you can see, this data right now is pretty wide. We're looking at about 18 or so radians. That's about 3 total revolutions here. And you can see that it's a little bit concave down. It's not really concave down, but a little concave down. And so it is not linear. This is an indication that though our apparatus is low friction, it's not no friction. So let's start zooming in. Let's zoom in to one full rotation. So I'm going to click here and edit my graph so that the time ends at, instead of 33.6, let's bring it down to 29.6. And excellent. And this will top our maximum angle so that our angular displacement is 2 pi, or 6.28 radians. All right, let's see what this looks like. You can see this looks much more linear. It still might be a little bit curved, but it looks much more linear. And so I'll go ahead and apply a curve fit to this data. And it'll be a linear curve fit. And we can see that the slope of this line is about 3.5. And what are the units again? Radians per second. So this slope is the angular speed. This is the data that you want to use in your calculation for the rotational inertia. Okay, 3.5 radians per second. That would be what you should be using here. Looking a little bit closer, it looks like at the very, very beginning something interesting is happening. So I'm going to zoom in there as well, just to explore for fun. So again, I'm going to go to Graph Options, and I'm going to shrink the time down to just like 1/10 of a second. So we're going to go 27.7 seconds, and let's top this out at, go ahead and enter about 0.3 radians. Ooh, interesting. See, it's cool already. So this is the very initial part of the data that we collected, and you can see that it is concave up here. Well, if it was a position time graph, so if it was a linear position versus time graph, and it was concave up, that would tell you that the speed of the object was increasing over time. It would be accelerating, and there'd have to be a force in the same direction as that thing was moving. And so here, this isn't linear acceleration, but this is angular acceleration. This is where that projectile is exerting a torque on the apparatus because it started with no angular speed. You can see over here on the left-hand side of our screen, we have a slope of roughly 0, and then the slope increases to some positive value. And so our angular speed is changing. We end up with the angular acceleration, which makes perfect sense because that foam ball had to hit and push on the apparatus to get it to be moving. So this is that angular impulse that got the apparatus to start moving in the first place. Now keep in mind, there was a torque acting on the apparatus, but there was also torque equal in magnitude and opposite in direction acting on the foam ball. The foam ball should end up slowing down when it gets caught by the apparatus. And so those torques actually cancel out. There is no net torque on the system. There's a ball rod system or a ball apparatus system, and that is an internal torque. And so it does not change the total angular momentum of our system. All right, so next we will take our last bit of data, and then you guys can do the calculation.
Okay, so the last bit of data that you're going to need is the velocity or the initial velocity of the projectile. And so we'll take that data directly from the packaging, which is 27 meters per second. You should, bonus points, if you can find and locate your velocity that you experimentally determined in the first semester of this class. So some bonus points there, or if you don't have that, can't find it, 27 meters per second from the packaging, that will be our initial velocity of our point mass. Okay, so now you should have all the data needed in order to calculate the rotational inertia of our apparatus. Once you do that, make sure you have the right units. The units should end up being kilograms meters squared. So those are the units for rotational inertia. So you can verify that you have correct units at the very, very end. So now we need to extend that. So our extension is going to be to calculate the launch speed of a Nerf Elite strong arm projectile. These projectiles have a mass of 1 gram. So you're going to have to redo everything, but now you'll have the rotational inertia of our apparatus, and you won't know the launch velocity of this. You've never done that, and quite frankly, our packages are long gone for this, so I guess I could Google it, but I don't know what the launch velocity of this is. Let's take the rotational inertia we just calculated, reapply conservation of momentum, and work backwards to find the velocity of this new point mass. And again, this point mass has a mass of about 1 gram. So that's your challenge thing. You can do that on your own. Post your results in the comments below. Smash that like button, hit subscribe, ring the bell, all those good things. All right, that's all I got for you today. Great job, Wildcats. Keep on rocking and rolling. COVID-19, we're out.